Imagine a world completely sealed off from the sun for, well, 5.5 million years. The air is toxic, the water is acid. If you took a single breath, you'd be dead in minutes.
Yeah, absolutely.
And yet, crawling through the pitch blackness is an apex predator that has no eyes, hunting in a thriving alien ecosystem. Today, we're opening the door to the extreme, bizarre, and, unseen world beneath your feet. Welcome to the deep dive. We are taking a stack of natural history records, geological surveys, and extreme biological studies to completely rewire how you see a rock.
I mean, we really do suffer from a severe surface bias.
Oh, for sure.
We tend to view geology as just this static stage, right?
Yeah.
Just a foundation where biology and weather happen to play out.
Mm-hmm.
But the reality is that the ground beneath you is a dynamic, violently active engine.
It's alive.
Essentially, yeah.
Yeah.
The chemical makeup of the rock miles below your chair is actively dictating life and death on the surface. It operates as a hard drive, recording billions of years of cosmic history, while simultaneously deleting entire epochs from existence.
And that is the exact mission for this deep dive. To prove that the Earth is not just a passive canvas, we are going to track down the single rarest physical object on the entire planet.
Which is a wild story.
It really is. And we'll explore the mechanisms of those toxic underground ecosystems that might actually hold the key to surviving our modern medical crises. And then we'll pull all the way back to analyze massive planetary scars visible only from orbit.
To really try and understand the terrifying concept of missing time.
Missing time. I love that.
Yeah, the common thread pulling all of this together is preservation versus erasure. We are looking at the miraculous chemical anomalies that survive the brutal churn of the Earth's crust. And, well, what the surviving physical evidence tells us about the sheer scale of geological time.
So let's start with the ultimate anomaly of preservation. To grasp the vastness of planetary geology, I think we need to zoom all the way into a microscopic scale.
Down to a single stone.
Exactly. We are talking about kyathite, officially the rarest mineral on Earth. And when I say rare, I don't mean diamond-level rare. There is exactly one specimen.
One single piece of kyathite exists in the known universe.
And the story of its discovery really highlights the chaotic nature of mineralogy. It was found back in 2010 by miners in the Chongi Valley near Mogok, Myanmar.
Right.
These miners were just sifting through river gravel looking for sapphires, which are pretty common in that region.
Yeah.
And they pulled up this water-weathered crystal.
But it didn't look like anything special, right?
No, not at all. It didn't look particularly spectacular in its rough form, maybe like a piece of amber or, topaz. So they simply tossed it in a basket and sold it at the local gem market.
Enter Dr. Kayathu, a Burmese mineralogist. He buys this rough, rust-colored stone.
Right, because he notices something off about it.
Exactly. He realizes it's incredibly dense, like heavier than most metals with this unusual metallic sheen to it. So he cuts and facets it into a tiny 1.61 carat orangish-brown gemstone.
And then the mystery really starts. Yeah, because when he tries to classify it, running it through all the standard spectrographic analyses, he gets no match. Zero record of its composition anywhere in the scientific literature.
Right, so Dr. Kayathu eventually collaborated with the International Mineralogical Association to determine its actual atomic structure.
Mm-hmm.
And they discovered it was a completely novel union of bismuth and antimony oxides.
It's totally unheard of.
Completely. The chemical formula is BisB4.
Okay, I'm struggling to understand the math here.
Yeah.
You're telling me that in Mogok, a region with, over 1,000 active mines?
So easily.
Churning up the Earth every single day for centuries, and they've only found one of these. Statistically, isn't it vastly more likely that this came from a meteorite? Or that it's some bizarre synthetic byproduct from industrial runoff, rather than a naturally occurring thing?
That is a completely valid skepticism, and it's exactly what peer review demands in these situations. To rule out a synthetic origin, or a meteorite, we have to look at the crystallography. Kyathite possesses a very distinctive three-dimensional tetragonal framework. It requires a highly specific geological perfect storm to crystallize naturally like that.
What kind of perfect storm?
Well, minerals form based on the availability of chemical ingredients, temperature, pressure, and time. So first, bismuth is an incredibly heavy element and is simply not a major component of most gem-forming regions in the crust.
Right.
And antimony is also relatively scarce. So to get them to bond in this exact tetragonal structure requires an environment where they are forced together under highly specific thermobaric conditions.
It's in pressure.
Exactly. And they have to remain undisturbed by the violent shifting of the crust long enough to actually crystallize.
So it's not just having the right ingredients, it's having the oven set to the exact fraction of a degree for like a million years, while the kitchen around you is actively burning down.
That is the perfect analogy for the geology of Mogok. I mean, if you drive into northern Myanmar, the highway signs literally read, "Welcome to Ruby Land."
I love that.
The sheer diversity of minerals there is staggering. George Harlow from the American Museum of Natural History described the region as a jaw-dropping geological mixing bowl. And the reason for that mixing bowl explains why Kyathwite could form there and literally nowhere else.
So what's the mechanism? What is driving that specific mixing bowl?
It is the brutal collision of multiple geological environments over deep time. First, you have igneous intrusions.
Magma.
Right, magma from the mantle pushing up into the crust, superheating and melting the existing rock. This forms pegmatites, which gives us sapphires and moonstones.
Okay.
Then, about 200 million years ago, tectonic forces smashed landmasses together, creating immense mountain-building pressure. This pressure took ordinary limestone and metamorphosed it into marble.
Creating rubies and spinels in the extreme heat.
Exactly. So you have magma cooking the rock and tectonic plates crushing the rock.
Sounds like a mess.
It is. And then you add a third mechanism, ancient hydrothermal fluid circulation. Millions of years ago, superheated water, pressurized deep underground, circulated through these crushed fault lines.
What does the water do?
It acts as a highly aggressive solvent. It dissolved trace elements, like our rare bismuth and antimony, transported them through rock veins, and then, as the water cooled or the pressure changed, it reprecipitated those elements into new crystalline structures.
And then weathering finally washes it all down into the Irrawaddy River Basin for a miner to just, scoop up.
Just scoop right up.
So the Earth spun a geological slot machine with a billion variables, and the bismuth antimony cherries lined up exactly one time.
Based on our current terrestrial surveys, yeah.
Yeah.
With a Mohs hardness of 6.5, Kyathwite is hard enough to survive some weathering, but it wouldn't survive the deep mantle churn forever.
Where is it now?
It currently resides at the Natural History Museum of Los Angeles County. We can't even run comprehensive destructive testing on it because doing so would literally erase the only known sample in existence.
Wow. So the Kyathwite stone is this miracle of chemical rarity. But it makes you wonder, if a hyperspecific matrix of rock miles below the surface can dictate the creation of a singular gemstone, how does everyday, common rock dictate the everyday world we live in?
That's a great question.
We need to talk about Dr. Richard Ott's global synthesis on lithology.
Yes. Dr. Ott from the GFZ German Research Center for Geosciences published this massive study that empirically proves bedrock, the solid rock underlying loose deposits like soil, dictates global topography, vegetation density, and animal biodiversity.
This challenges everything I thought I knew about ecology, honestly.
How so?
Well, if I look at a dense, lush forest in the mountains, I assume the ecosystem is there because of the climate, high rainfall, good sunlight, maybe wind patterns. The rain dictates the plants dictate the animals.
Right, that's the standard assumption.
But you're saying the chemical makeup of the literal bedrock miles underground is actually the invisible architect pulling the strings.
The climate is a factor, of course. But Ott's high-resolution global maps of the rock subsurface, when they correlated them with satellite vegetation data, showed that rock properties are the foundational constraint on what can live above them.
Fascinating.
The primary mechanism comes down to chemical weathering and soil hydrology. Let's look at plutonic rocks like granite or sedimentary clay stones.
Okay, let's unpack the mechanism. How does a solid sheet of underground granite translate into a higher population of frogs and amphibians on the surface?
It starts with chemical weathering, specifically hydrolysis. Granite contains a high amount of a mineral called feldspar.
Okay.
When rainwater, which is naturally a very weak carbonic acid, seeps through the topsoil and hits that granite over thousands of years, it chemically reacts with the feldspar. This reaction transforms the hard mineral into kaolinite.
Which is clay.
Exactly, clay.
And clay has an incredibly high water retention capacity.
Down to its microscopic structure, clay minerals form in these incredibly fine microscopic tetrahedral sheets.
They hold water really well.
Right, these sheets have an enormous surface area and carry a slight negative electrical charge.
Yeah.
This strongly attracts and binds the polar water molecules. So a granite bedrock weathers into a thick, clay-rich soil that acts like an immense subterranean sponge.
Ah, a sponge.
Because the water sticks around, you get continuous, lush vegetation even between rainfalls. And because you have a stable, moisture-rich environment, you see a massive spike in species diversity, particularly vertebrates and amphibians that require high ambient moisture to survive.
So the amphibians are there because the granite forces the creation of a sponge. Now, what happens when you swap out the bedrock? What if we have limestone instead?
We get an entirely different biome. Limestone bedrock creates karst landscapes. Limestone is primarily calcium carbonate. It doesn't weather into a spongy clay.
So what does it do?
Instead, the slightly acidic rainwater slowly dissolves the limestone along existing fractures, widening them into massive, highly porous fissures and underground drainage systems.
You essentially turn the bedrock into Swiss cheese.
Precisely the structural result. When it rains on a karst landscape, the water doesn't pool in the soil. It instantly drains away, plummeting deep underground through those fissures.
Oh, wow.
The surface topsoil dries out almost immediately. These regions also struggle to hold on to nutrients as they are constantly flushed down the literal geological drain.
Right, because there's no clay to hold anything.
Exactly. Consequently, the vegetation is sparse, creating bare, rocky landscapes. Think of the coastal mountains in Croatia or the dry, rugged hills of Greece. Ott's biological data overlay proved that these rapid drainage limestone areas support significantly fewer species of birds, mammals, and amphibians compared to their water-retaining granite counterparts in the exact same climate zones.
That is profoundly humbling. The birds in the sky are literally constrained by the calcium carbonate in the ground. And Dr. Ott also found that this bedrock dictates the physical shape of the planet itself, right? The steepness of the mountains.
Yes. His analysis of topography disrupted the prevailing theory that climate primarily determines how steep a mountain can get.
Wait, really?
Yeah, the assumption was that heavy tropical rain would erode a mountain faster, leading to gentler slopes over time compared to, say, a dry desert mountain. Ott found no concrete global evidence for climate-dominating topography. Instead, rock durability overrides everything.
The tensile and shear strength of the bedrock itself.
Hard rocks, like granite and solid limestones, have high internal cohesion. They can physically resist the shear stress of a flowing river or a collapsing slope. Therefore, they can support much steeper angles before failing.
But soft rocks can't.
Right. Soft rocks, like shales or claystones, have low internal friction and slump under their own weight when pushed to high angles. The bedrock dictates the posture of the Earth's skeleton, entirely regardless of the atmospheric clothes it happens to be wearing.
So we have bedrock chemically weathering to nurture life on the surface. But let's flip that concept.
Right.
What happens when the rock doesn't nurture life but actively buries it? What happens when geological formations sever an ecosystem from the sun entirely, leaving biology to fend for itself in the dark?
We enter the domain of extreme evolutionary biology, places where life has abandoned photosynthesis and embraced chemical warfare.
We are going to Movile Cave in Romania, near the Black Sea. Discovered entirely by accident in 1986 by a geologist named Cristian Lascu during an assessment for a power plant.
Right, they were just doing routine work.
Yeah, they sank a shaft into the ground, broke into a void, and found an environment that had been hermetically sealed by thick layers of clay and limestone for 5.5 million years.
To contextualize that deep time, the ancestors of modern humans, the Australopithecines, were just beginning to experiment with bipedalism in Africa when the geological door to Movile Cave slammed shut.
It's hard to even picture that.
It has been utterly isolated from the Earth's surface ever since.
And the environment inside is incredibly hostile. The temperature sits at a stagnant 70 degrees Fahrenheit or 21 degrees Celsius with 100% humidity.
Uncomfortable, but not deadly.
Right, but the atmosphere is a nightmare. It is severely hypoxic. The oxygen level is barely a third of what we breathe on the surface. Meanwhile, carbon dioxide is 100 times higher than normal.
Wow.
The air contains explosive levels of methane, and the submerged hydrothermal waters filling the lower levels of the caves are saturated with highly toxic hydrogen sulfide and ammonia.
Yeah, a human would suffocate and succumb to hydrogen sulfide toxicity within a matter of minutes.
Absolutely.
Yet, despite being a pitch-black toxic gas chamber, Movile Cave is teeming with life. Researchers have identified 57 distinct animal species inside, 37 of which are completely endemic to that specific cave system.
Okay, stop right there. I need you to explain the fundamental energy mechanism here.
Sure.
Because above ground, the sun provides photons. Plants use those photons to convert carbon dioxide into glucose. Bugs eat the plants. Birds eat the bugs. The sun is the battery.
Right.
Down in Movile, there are no photons. There are no plants.
Yeah.
How is this food web not violating the laws of thermodynamics? Where is the caloric energy coming from?
The energy comes from the poison itself.
From the poison.
Yeah, through a mechanism called chemosynthesis. It is similar to what we see at deep-sea hydrothermal vents. The base of the Movile food web is driven by aerobic elemental sulfur-oxidizing bacteria, as well as methane-oxidizing bacteria.
How exactly do they eat sulfur? That sounds insane.
These microbes possess specific enzymes that allow them to strip electrons from the toxic hydrogen sulfide gas.
Okay.
They use the energy released by those electron transfers to power their own internal cellular machinery, essentially running their version of the Krebs cycle, converting the abundant carbon dioxide in the cave into organic cellular carbon.
So they literally transform toxic gas into physical biomass.
Yes, like they grow into these thick, yellowish-white microbial mats or biofilms that float on the surface of the hydrothermal pools and coat the limestone walls.
So the biofilm acts as the grass of the cave.
You could say that, yeah.
And grazing on this toxic grass is a menagerie of horrors. We're
Mhm.
talking about blind spiders, leeches, water scorpions like Nipa anaphthalma.
Yeah, the biodiversity is crazy.
And sitting at the absolute top of this food chain, the apex predator is a centipede.
Cryptops speleorex. It's a remarkably aggressive invertebrate that patrols the cave walls, hunting down the smaller isopods and springtails that graze on the bacterial mats.
What fascinates me is the sheer evolutionary efficiency of these creatures. Over 5.5 million years, they haven't just adapted to the dark. They have physically deleted traits they no longer need.
Right, because vision is biologically expensive.
Very expensive.
Maintaining optic nerves and visual cortexes requires a significant caloric investment. In complete darkness, those calories are wasted. Consequently, natural selection rapidly favored individuals that reallocated that metabolic energy elsewhere.
So they just got rid of their eyes.
Almost all the endemic species in Movile are completely anophthalmic. They have no eyes whatsoever. Furthermore, they lack pigmentation, rendering them a translucent, ghostly white. Because producing melanin to protect against UV radiation is similarly useless.
But they must have compensated in other ways to hunt in the dark. You can't just be blind and hope for the best.
Drastically.
Mm-hmm.
They evolved extraordinarily elongated antennae and appendages packed with highly concentrated mechanoreceptors and chemoreceptors.
Oh, like super sensors.
Exactly. They perceive their world through minute changes in air pressure, water vibrations, and chemical gradients. And physiologically, their respiratory systems have hyper-adapted to extract oxygen from an atmosphere that barely has any.
While swimming in poison.
Right, while simultaneously neutralizing the severe toxicity of the hydrogen sulfide penetrating their tissues.
Now, the sources mention an incredible symbiotic relationship involving the groundwater amphipods, specifically Nephargus cf. Stygius. They are literally teaming up with the sulfur bacteria to survive.
It is a stunning example of ectosymbiosis. Researchers observed these amphipods covered in a dense fur of Theothrix bacteria.
Fur, like a bacterial coat.
Yeah, these bacteria are physically attached to the spines and hairs of the amphipod's legs and antennae, and genetic sequencing revealed a crucial detail. The bacteria living on the amphipods are genetically distinct from the free-floating biofilm on the cave walls.
Wait, so they evolved specifically to be passengers?
Exactly. They are specialized epibionts. The mechanism likely involves the amphipod acting as a transport vehicle, moving the bacteria through different chemical gradients in the water to maximize the bacteria's access to hydrogen sulfide and oxygen.
And what does the amphipod get out of it?
In return, the bacteria might be detoxifying the immediate microenvironment around the amphipod or providing a direct nutrient source. It's an incredibly complex biological economy entirely divorced from the sun.
Movile Cave is an alien world that evolved horizontally to us, but it's not the only extreme underground environment forcing radical biology. Let's travel from the Black Sea coast to the Chihuahuan Desert in New Mexico to Carlsbad Caverns National Park.
Okay, Lechuguilla Cave.
Yes, I want to look at Lechuguilla Cave because the biology hiding down there directly impacts modern human medicine.
Lechuguilla operates on a staggering scale. It is the 9th longest explored cave on the planet, with over 150 miles of mapped subterranean passages, plunging nearly 1,600 feet into the earth.
And what's wild is that until 1986, nobody knew the vast majority of it was there. It was just a small 90-foot pit called Misery Hole, where miners historically dug out bat guano.
Right.
But local cavers kept noting this massive roaring wind blowing up from the rubble at the bottom of the pit.
Which is a huge tell. In speleology, a sustained high-volume wind roaring out of a small hole is the ultimate indicator of vast barometrically pressurized void spaces deeper underground.
So they dug.
When a team from the Colorado Grotto finally excavated through the rubble in 1986, they bypassed the surface entirely and broke into an unimaginably vast labyrinth.
And the sheer scale of the void space immediately presented a geological mystery because of how the cave was hollowed out.
Right, because typical limestone caves like Mammoth Caves are formed from the top down by carbonic acid in rainwater dissolving the rock over millions of years.
But the geology of Lichugia didn't match top-down erosion.
Not at all. It was hollowed out from the bottom up through a highly aggressive process called speleogenesis by sulfuric acid dissolution.
Bottom up.
Yeah, deep beneath the Guadalupe Mountains lies the Delaware Basin, which holds vast ancient petroleum deposits. Millions of years ago, hydrogen sulfide gas migrating upward from those oil reserves intersected with the highly oxygenated water table resting in the limestone.
And when the gas hits the oxygenated water, it chemically reacts to create massive amounts of highly concentrated sulfuric acid.
And that sulfuric acid violently ate away the limestone from below, hollowing out immense chambers and leaving behind massive deposits of gypsum. This aggressive chemical environment resulted in some of the most bizarre and delicate speleothems ever discovered. We see 20-foot-long solid gypsum chandeliers hanging from the ceiling, delicate strands of hydromagnesite known as cave balloons, and brilliant lemon-yellow sulfur deposits.
It's an underground cathedral carved by acid. But the true significance of Lechugia isn't the gypsum chandeliers, it's the invisible biological war raging in the soil. Because, just like Movile, Lechugia is highly isolated, incredibly nutrient-poor, and populated by chemolitho-autotrophic bacteria feeding on sulfur, iron, and manganese.
And this brings us to one of the most profound medical discoveries of the 21st century.
This is the craziest part.
We are currently facing a global antibiotic resistance crisis. Decades of overprescribing penicillin and synthetic antibiotics in agriculture and medicine have forced bacteria to rapidly evolve into highly resistant superbugs.
Yeah, it's a huge problem.
And the assumption has long been that antibiotic resistance is a strictly modern anthropogenic crisis, a problem entirely created by human interference.
Until microbiologists took soil samples from deep inside Lechugia Cave.
Precisely. Researchers isolated a highly specialized strain of bacteria called Paenobacillus from a deeply remote section of the cave.
Okay.
Geological dating confirms this area of the cave has been physically isolated from the surface for over 4 million years. The water dripping into this chamber hasn't seen the surface since the Pliocene epoch.
So long before humans.
Right. This Paenobacillus strain has never encountered a human being, let alone a modern hospital or a synthesized pharmaceutical compound.
Wait, before we move on, if a bacteria has never seen a modern hospital, how exactly is it defending itself against our modern synthesized drugs?
Well,
Because the studies showed this 4 million-year-old microbe is naturally aggressively resistant to roughly 70% of modern antibiotics, including daptomycin, which is our heavy-duty drug of last resort. What is the actual chemical shield it's using?
it utilizes highly sophisticated enzymatic degradation and target modification. Let's look at daptomycin. Daptomycin is a lipopeptide antibiotic. It works by inserting itself into the bacterial cell membrane, aggregating and literally poking massive holes in the membrane, causing the cell to rapidly lose ions, depolarize, and die.
Like a chemical spear that pops the cell?
Yes. The Paenobacillus strain in Lechugia defends against this by actively altering the electrical charge of its own cellular envelope.
What?
It modifies the lipid molecules in its membrane to increase the positive charge on its surface. Because daptomycin molecules also carry a positive charge, the modified bacterial membrane electromagnetically repels the antibiotic molecule before it can even attach.
The spear bounces off the force field?
Furthermore, against other drugs, this ancient bacteria deploys dedicated efflux pumps, literal microscopic protein motors embedded in its cell wall that recognize antibiotic molecules and physically pump them back out of the cell before they can do damage.
It's deploying force fields and biological bilge pumps against drugs we literally invented in a lab 10 years ago. Why would a bacteria locked in a cave for 4 million years possess the genetic blueprint to defeat human pharmacology?
Because antibiotics are fundamentally natural weapons. In the brutal, starved environment of a deep cave, microbes have been locked in extreme chemical warfare with fungi and competing bacteria for millions of years.
Oh, I see.
To secure scarce resources, one species evolves a toxic compound to kill its neighbor. To survive, the neighbor evolves an efflux pump or a modified membrane to resist that specific toxin.
It's an arms race.
The genes governing antibiotic resistance didn't magically appear in modern hospitals. They have been weaponized and refined in subterranean battlegrounds for eons. We merely stumbled into an ancient war, and our synthetic drugs happen to trigger the exact same defense mechanisms these microbes perfected millions of years ago.
So the cure to our modern superbug crisis, or at least the roadmap to outmaneuvering them, requires us to study the genetic libraries locked away in extreme geological isolation.
Unquestionably, untouched geology preserves the undisturbed biological history of the planet.
We've been zooming in on microscopic mineral grids in Myanmar, on cellular efflux pumps in underground bacteria. Now, I want to radically shift our perspective. Let's talk about the macro level.
Sounds good.
I want to pull back into orbit and look at the massive scars, domes, and structures left behind by tectonic forces over deep time. Things so colossal you can only perceive their true nature from space.
We're transitioning from the timeline of biology to the timeline of planetary mechanics. And the premier visual representation of this is the Richat structure in the Sahara Desert of Mauritania.
The Eye of the Sahara. It's a 25-mile-wide, perfectly circular rock formation sitting utterly isolated in the endless sand of the Western Sahara. It looks exactly like a colossal bullseye.
It really does.
It's so massive and geometrically precise that astronauts aboard the Gemini and Apollo missions routinely used it as a visual landmark for orbital navigation.
And for decades, the sheer circular perfection of the Richat structure led the scientific community to the most logical assumption that it had to be an astrobleme, an impact crater from a massive meteorite strike.
Right, because what terrestrial mechanism makes a 25-mile-wide perfect circle? But when geologists actually went in on the ground, the impact theory completely fell apart. Why?
The absence of shock metamorphism.
What's that?
Well, when a meteorite strikes the Earth, the kinetic energy transfer generates unimaginable localized heat and pressure, pressures exceeding millions of atmospheres in a fraction of a second. This leaves very specific, unmistakable forensic evidence in the rock.
Like what?
We find highly shocked quartz, a high-pressure polymorph of silica called coesite, and large volumes of melted vitrified rock called swavite.
The blast literally permanently alters the atomic structure of the target rock.
Exactly. But when Professor Michel Jabrac from the University of Quebec, along with an international team of geologists, comprehensively mapped the Richat structure, they found none of this.
No.
There was no coesite, no shocked quartz, no massive melt sheets. The rocks were simply folded and fractured, not vaporized by an impact.
So if a massive rock didn't smash into the crust from above, what pushed up from below?
A colossal diapir of magma. The Eye of the Sahara is actually a deeply eroded 100-million-year-old volcanic blister.
A blister.
To understand the mechanism, we have to rewind the clock to the late Cretaceous period, during the violent breakup of the supercontinent Pangaea. As the African and South American tectonic plates were tearing apart to form the nascent Atlantic Ocean, the Earth's crust in this region was subjected to extreme extensional stress. It was stretching and thinning.
And as the crust thins, the pressurized mantle below sees a weak point.
Yes. A massive plume of highly pressurized magma began intruding upward from the deep mantle, but crucially, it never breached the surface to form a violently erupting volcano.
It just got stuck.
Right, the magma stalled out in the upper crust, spreading laterally. The immense hydraulic pressure of this subterranean magma chamber slowly forced the overlying horizontal layers of sedimentary rock upward, warping them into a massive 25-mile-wide dome.
Creating a gigantic geological blister.
And then the magma cooled, the uplift stopped. Over the subsequent 100 million years, relentless subaerial erosion, wind, water, and extreme temperature fluctuations in the Sahara sheared the top off the dome, grinding it completely flat.
And this explains the bullseye pattern.
Yes, through differential erosion. Because the rock layers were pushed up into a dome, slicing the top off horizontally exposes the layers in concentric rings, like slicing the top off an onion.
Oh, that makes so much sense.
The harder rocks, like tough quartzites, resist erosion and form the high, raised ridges of the bullseye. The softer sedimentary rocks erode much faster, forming the deep valleys between the rings.
And the types of igneous rocks exposed in the very center of the eye tell us just how deep this magma plume originated, right? We're not just looking at surface lava.
No, we're looking at a deep cross-section of the Earth's plumbing system. The center of the Richat structure contains rhyolites and gabbros, but significantly, it contains carbonatites.
What are those?
They're an incredibly rare type of igneous rock formed from carbonate-rich magma originating roughly 30 to 40 miles deep. Even more astoundingly, there are kimberlite plugs nearby.
Kimberlite.
Kimberlite magma originates at profound depths, often exceeding 125 miles down in the mantle. The Eye of the Sahara is effectively a 125-mile-deep core sample of the Earth's mantle, pushed to the surface and laid out perfectly flat in the desert for us to read.
It is a geological masterpiece. But if we want to talk about true ancient giant structures that defy our very conception of time, we have to leave Mauritania and head to the Australian outback.
Yes, Australia.
Australia is fundamentally a continent defined by extreme deep time and the megaliths that survive it.
The Australian craton is one of the oldest, most stable pieces of continental crust on the planet, and the structures that rest upon it are staggering. Let's analyze the structural mechanics of Uluru, formerly known as Ayers Rock.
It's perhaps the most iconic rock formation on Earth. A massive monolithic fin of red sandstone rising abruptly out of the flat desert, standing 1138 feet high, with a circumference of nearly 6 miles.
Massive.
And that's just the tip. Geologists estimate the bulk of the rock extends over 1.5 miles straight down beneath the sand.
The sheer volume is impressive, but the structural orientation is what makes Uluru a marvel of tectonic violence. The specific rock that comprises Uluru is Arkose sandstone, heavily laden with feldspar.
Okay.
This sand was originally deposited horizontally, layer upon flat layer, at the bottom of an ancient inland sea during the Cambrian period, roughly 500 million years ago.
But if you look at the face of Uluru today, those sedimentary layers, the strata, aren't flat. They are vertical. The lines run straight up and down into the sky. How does a miles-long solid block of horizontal rock get flipped 90 degrees without completely shattering into dust?
The mechanism is called the Alice Springs orogeny. Between 300 and 400 million years ago, immense tectonic plate collisions slowly applied unimaginable relentless lateral compression to the Australian crust.
Right.
The bedrock didn't just snap. Over millions of years, the heat and pressure made the rock slightly plastic. The entire horizontal seabed was violently folded, buckling like a rug pushed against a wall. The massive block of Arkose sandstone that would become Uluru was physically shoved onto its side, rotating a full 90 degrees until the horizontal strata became vertical.
And then hundreds of millions of years of erosion stripped away the softer surrounding rock, leaving this impossibly hard vertical fin exposed. And just 15 miles away, you have Katajuta, the Olgus, which looks completely different. It's a collection of 36 massive, rounded domes, the tallest of which dwarfs Uluru by nearly 650 feet.
The visual contrast is stark because the lithology is different. Katajuta is not sandstone, it is conglomerate rock.
Explain conglomerate.
As the ancient mountains were thrust upward during the Peterman orogeny 550 million years ago, they immediately began eroding at a catastrophic rate. Massive alluvial fans of boulders, cobbles, and mud washed down into deep troughs.
Like ancient avalanches.
Over deep time, this chaotic rubble was heavily compressed and cemented together by silica and iron oxide into an incredibly tough conglomerate rock. Katajuta is essentially ancient, petrified avalanche debris carved into domes by chemical weathering along structural fractures.
But even Uluru and Katajuta are infants compared to what sits in Western Australia. We have to talk about Mount Augustus or Burringura.
Mount Augustus fundamentally distorts our perception of scale. It is effectively twice the size of Uluru.
Twice the size.
It's a colossal mountain over 5 miles long, towering 2,800 feet above the surrounding plain. Structurally, it is an asymmetric anticline, a massive fold in the rock strata. The sandstone and conglomerate comprising the mountain itself are estimated to be 1 billion years old.
1 billion years.
And the granitic bedrock it rests on, the basement rock of the continent, is firmly dated at 1,650 million years old.
See, this is where my cognitive ability to comprehend time completely glitches out. 1 million years is impossible to visualize. 1 billion years is abstract nonsense to the human brain. How do geologists actually prove a rock is 1,650 million years old? How do they know it's not 1,500 million or 2,000 million? What is the physical mechanism behind measuring deep time?
The absolute measurement of deep time relies on isotopic geochronology, and the gold standard for dating ancient crustal rocks is an incredibly sophisticated piece of technology called the Sensitive High-Resolution Ion Microprobe, or the SHRIMP.
I absolutely love that the machine unlocking the secrets of the cosmos is named the SHRIMP. Walk me through exactly how this time machine works.
It centers on a microscopic mineral called zircon. Zircon crystals are essentially indestructible. They can survive being subjected to extreme magma temperatures, intense tectonic crushing, and billions of years of abrasive weathering.
Tough little crystals.
But their true value lies in their atomic structure when they first crystallize from cooling magma.
They act as atomic vaults.
Precisely. The chemical formula for zircon is ZrSiO4. During crystallization, the crystal lattice gladly accepts atoms of uranium because the uranium ion has a similar size and a 4+ charge, perfectly substituting for zirconium.
Okay, so it takes in uranium.
However, the lattice violently rejects lead atoms. Lead ions are too physically large and have a 2+ charge. They simply cannot fit into the structural grid.
Oh, so at the exact moment a zircon crystal hardens at hour 0, the vault is sealed with uranium locked inside and mathematically 0 lead.
Exactly. But uranium is a radioactive isotope.
What?
Over immense spans of time, the uranium-238 inside the crystal undergoes alpha and beta decay, eventually transforming into stable lead-206.
And that decay rate is constant.
The mechanism of this radioactive decay is governed by the strong nuclear force. It is a universal constant. It is completely unaffected by the heat, pressure, or chemical changes happening to the rock outside. The decay rate operates as a flawless, unstoppable atomic clock.
So any lead found inside that crystal later must have come from the decay of the trapped uranium.
Yes. And this is where the shrimp comes in. The shrimp uses secondary ion mass spectrometry. A scientist takes a microscopic zircon extracted from Australian bedrock and places it in a vacuum chamber.
Right.
The machine fires a highly focused beam of oxygen ions directly at the crystal, literally sputtering away a tiny fraction of the surface, atom by atom. The machine then analyzes the mass of the ejected ions, precisely counting the exact ratio of remaining uranium atoms to the newly generated lead atoms.
Because they know the exact half-life of uranium-238, which is about 4.5 billion years, they simply apply the math to that ratio to determine exactly when the vault was sealed.
And using the shrimp, geologists analyzing sandstone from the Jack Hills in Western Australia found detrital zircon crystals that date back an incomprehensible 4.4 billion years.
Of that.
The Earth itself is estimated to be roughly 4.54 billion years old. We are holding tiny, indestructible crystals that formed almost immediately after the planet's magma ocean began to cool into a solid crust.
It's deeply profound. The Earth has been meticulously keeping its own time in microscopic crystal clocks since the violent dawn of the solar system. The rock remembers everything.
It does, but that raises a terrifying counterpoint. We just established how geology perfectly preserves chemistry, biology, and time. What happens when the physical record itself is physically deleted?
What do you mean?
What happens when the rock forgets?
We are talking about the concept of missing time. To explore this, we need to go to the Tirumala Hills in the state of Andhra Pradesh, India. We're looking at a geological feature called the Natural Arch, or Silatharanam.
Sila translates to rock, and Tharanam to a garland or an arch strung over a threshold. It is a striking, naturally formed quartzite arch, roughly 26 feet wide and 10 feet high, located just a kilometer from the profoundly sacred Tirumala Venkateswara temple.
The cultural and religious mythology seamlessly interwoven with this rock formation is beautiful. There are multiple interpretations. One states the arch physically resembles the hood of a divine serpent, a conch shell, and a discus, all of which are potent symbols of worship in the Hindu tradition. Another tradition points out that the height of the arch perfectly matches the height of the main deity inside the Tirumala temple.
The most geographically evocative legend asserts that the arch is quite literally a divine footprint. The mythology dictates that Lord Vishnu, as Lord Venkateswara, descended to earth, placing his first step on the highest peak of the Tirumala Hills at Uluru.
Okay.
His second step came down exactly on the location of the natural arch, and his final step was placed where his idol is now venerated in the temple.
The landscape is inscribed with the movement of the divine, but underneath that rich theological history, the very rock the arch is made of harbors a massive, violent geological secret.
In the 1980s, geological surveys were systematically analyzing the stratigraphy of the Tirumala Hills. The arch itself is composed of intensely hardened quartzite, which is sedimentary sandstone that has been heavily compressed and slightly metamorphosed.
So how did it form?
The actual hollowing out of the arch was achieved by intensified, localized wind and water weathering over the last 2.5 million years. But the structural anomaly wasn't how the arch formed. It was the exact boundary line the arch was resting upon.
It's sitting directly on top of a major fault line.
Specifically, an Aperchean unconformity. Geologists analyzed the sequence of the rock layers. The top layer, the quartzite forming the arch and the immediate ground beneath it, belongs to the Cuttapah supergroup. Isotopic dating confirms these sedimentary rocks were laid down in an ancient, shallow marine basin approximately 1,600 million years ago.
Okay, 1.6 billion years old. That's the top layer.
But the crystalline basement rock resting immediately, directly beneath that sedimentary layer, a complex mix of Archean granites, gneisses, and dolerite dikes, dates to more than 2,100 million years ago.
I need you to clarify the math here. We have 1,600 million year old rock resting cleanly and directly on top of 2,100 million year old rock. There's a staggering gap. Where did the missing 500 million years of rock go?
That gap is the physical definition of unconformity. It represents a massive discontinuity in the geological record. Stratigraphy dictates that rock layers act like pages in a history book, deposited sequentially over time.
Layer by layer.
But the Earth's crust is in constant vertical motion due to aperigenic forces. Imagine that 2,100 million years ago, this region was a stable crustal block. But then, immense tectonic forces uplifted the entire region high above sea level.
And the moment rock is exposed to the atmosphere, the recording stops and the erasing begins.
Exactly. Deposition ceases and brutal subaerial weathering takes over. For 500 million years, this entire landscape was continuously battered by rain, wind, chemical dissolution, and river erosion.
That's a lot of weathering.
500 million years of potential mountains, entire ancient ecosystems, and the evolutionary history of early Proterozoic life were aggressively ground into microscopic dust and washed away into the global oceans. The physical evidence of that entire half-billion-year epoch was utterly, totally deleted from the continent.
It's like finding a pristine Roman Colosseum built directly on top of a 1990s subway station. The chronology is so violently broken that your brain struggles to process the missing era.
That is a highly accurate way to visualize it. The Eparchian unconformity is the physical scar of that missing era. After 500 million years of relentless erasure, tectonic forces caused the region to subside back down below sea level.
And then the recording starts again.
A new, shallow basin formed over the heavily eroded Archean bedrock, and the 1,600 million-year-old Cutipus sediments finally began to pile up, sealing the gap. The unconformity is a stark reminder that the geological record we rely on is terrifyingly fragile. We only have access to the history the Earth chose not to destroy.
The rock is a hard drive, but it routinely formats itself. Let's pull all of this together because the sheer scale of what we've discussed today demands a fundamental shift in perspective.
It really does.
We started at the absolute microscopic limit of preservation, tracking down a single 1.61 carat piece of cowthwaite in Myanmar, a mineral forced into existence by a hyperspecific, unrepeatable collision of magma, crushing pressure, and superheated fluid.
We moved from a chemical anomaly to the everyday chemical power of global bedrock. We explored Dr. Ott's proof that the invisible lithology miles underground, whether it weathers into water-trapping clays or porous karst fissures, is the ultimate architect dictating the topography of our mountains and the biodiversity of our forests.
We journeyed into the terrifying hypoxic darkness of Movile Cave in Romania, where a 5.5 million-year-old ecosystem abandoned the sun entirely, thriving on toxic hydrogen sulfide and evolving into a menagerie of blind, specialized predators.
We analyzed the ancient chemical warfare in Movile Cave, realizing that the key to defeating modern superbugs might lie in the cellular force fields of bacteria isolated for 4 million years.
And we expanded our view to planetary mechanics and deep time. We analyzed the 100 million-year-old magma diapir creating the Eye of the Sahara.
The billion-year-old tectonic violence that folded the megaliths of Australia.
And the atomic perfection of zircon crystals tracking the age of the Earth. Finally, we confronted the terrifying abyss of the Eparchian unconformity, a literal line in the rock where 500 million years of planetary history was violently erased from existence.
The ultimate takeaway for you, the listener, is that you're not standing on inert dirt. The ground beneath your feet is a volatile, constantly processing chemical engine.
Every grain of sand, every jagged mountain peak, every limestone cliff is actively telling a story of unimaginable pressure, biological warfare, and vast spans of deep time. The geology of this planet is alive.
It forces us to acknowledge that the Earth's surface is merely a temporary crust over a deeply active, poorly understood mantle.
And that leads to a profound final thought. We've seen that a 4 million-year-old cave bacteria holds the evolutionary key to defeating our modern antibiotic crisis. We've seen that a billion variables align to produce exactly one piece of cowthwaite in human history. If the Earth is capable of hiding these profound, singular miracles just a few miles beneath our feet, What unimaginable geological structures, what impossible chemical minerals, and what bizarre alien forms of life are violently crystallizing right now, deep in the crushing pressures of the Earth's mantle, just waiting for the tectonic plates to shift and thrust them to the surface for the next generation of explorers to find.
We have barely scratched the surface of what the Earth is actively building.
Keep digging. We'll catch you next time on The Deep Dive.